Welcome back my dear students, my dear friends, and this is the project management course which all of you are doing. And if you remember, in the 35th class I started the concept of GERT, told about the exclusive OR, the inclusive OR, the AND operators, and gave you the concept, the how three different combinations of the input and two different combinations of the output gives you all the picture of the GERT. And I also told you that the two important parameters based on which you will do the calculation was the probability. So, in the deterministic case the probability would be 1, and in the probabilistic one the probability would be less than 1. So, but obviously it means that all the addition of all the probabilities of all the paths which were plausible, which were possible, would add up to 1 logically, and obviously the time to traverse from node 1 to node 2 or node 2 to node 3 are probabilistic, considering that time taken is also not fixed. So, let us consider and these points and continue our discussion for the GERT. So, what are the steps in the GERT? The logical steps how you take into consideration to basically formulate the GERT are as follows. Convert a qualitative description of the system problem to a model in the input form. So, basically what you have is that whatever the information which you have, based on the information you convert them into a logical set of input and also a logical set of output, depending on what is the output coming out from the description of the problem, such that you are able to combine the inputs and the outputs in a very logical fashion to get the sets of inputs and outputs in the node form with arcs connecting them, and the arcs would be the if and only if, and the exclusive or inclusive or the concept of and all would be considered in order to basically give the most realistic picture, and obviously considering the fact that a looping would also be there. So, the second point as stated in this slide is that collect the necessary data to describe the branches of the network. So, you will try to basically collect the information to the maximum possible extent, such that it will give you actual practical picture, theoretically as intense picture as possible of the input, such that you are able to get the output in the most best possible manner. The word best possible manner means that logical statements should be taken into account, such there is no flaw in the overall flow process of the overall project, starting from the source to the sink. Source means from where you are starting, sink means when I am basically ending the overall project. Third point is obtain an equivalent one branch function between two nodes of the network. So, if say for example, there are two sets of activities and they are being linked, like grinding leads to the lathe operation, consider very hypothetically, or say for example, after finishing etching operation, consider then you will go to the painting booth. We are basically trying to manufacture some manufacturing machine, or you are trying to manufacture a machine, or say for example, you are trying to basically stitch a cloth into a shirt, you stitch it and then the buttons have to be put at the right place. So, these are two, I am considering very simple operations. Or say for example, you have made and you are trying to basically see how the project can be done, very simplistic problem, like you are trying to make ice creams at home, and then once you make the ice cream, all the milk and the vanilla and the sweet and the flavor has been added, the next logical step you put in the fridge. So, these are two logical steps. So, you have been able to draw these logical steps, this practical set of information into nodes as they are connected by edges with their maximum amount of information, which has two sets of information as I mentioned, one is the probability and one is the time, based on which these two parameters you will do all the calculations. The fourth point of the GERT steps, how you proceed to make the steps in the GERT is convert the equivalent function into the following two performance measure of the network. So, basically depending on the two inputs, you will want to basically finalize that how you will try to utilize these two inputs or parameters in order to finalize that how would you rank or how would you find out the overall working of the efficiency of the projects. One is The probability that a specific node is realized, that would come from the probability function. So, whether probability is 0.1, 0.2, it has something to do with the critical index, if you remember in the simulation of the PERT network, but it is not redirected, but I thought I will try to basically mention that such things are much clear. The second point is the moment generating function of time associated with an equivalent network. So, you will try to find out what is the moment generating function of the time, so that you can take that time function into consideration in order to find out the overall time for the project. And the last point is that make inference concerning the system under study obtained in 4, so that you can take a realistic decision how the overall project is undertaken, considering the probability, the time, the nodes are realized, not realized, looping is there, what is the logical inflow of input, what is the logical flow of the output, and all these things. Now, let us consider a very simple example in two different flavors. So, space mission consists of two vehicles. So, before I start off this, all of the problems are taken from the book. So, all the different references which I have taken. So, these two examples are taken from the Pritzker GERT book, and if you remember, I did mention that when we were discussing the reference list. So, you can find it in the net also, or you can find a hard copy of that in one of the nearest library in the locality where you belong. So, this is a space mission consisting of two vehicles. The second point which is very important to note is that both vehicles must be successfully launched in order to basically have success in the overall project. So, based on the statement, let me draw the diagram. So, what you have in front of you is the vehicle 1 and vehicle 2. So, these are triangles. So, if you go back, to the points of the input and output which we have done. So, this was basically there was one deterministic one was the probabilistic one for the outputs and the inputs, and there was an exclusive OR, inclusive OR, and the AND one. Based on that we proceeded. So, the successful launch, which is these two rows arrows which I have. So, this is the successful launch. This is the successful launch. So, this I will mark with a red, and the unsuccessful launch are this. So, these are marked in yellow. If you combine them, it says, let me again go back to the last slide to make things much clearer. Both the vehicles must be successfully launched, which means that consider there are 4 combinations. Yes for both stage 1, stage 2, that means both are successful. Yes, no for stage 1, stage 2, which is the vehicle 1 and vehicle 2. Case 3 is no and yes for vehicle 1 and vehicle 2, and the last one is no for both the vehicles 1 and 2. Now, if you consider that the sequence is coming and it is being described in this diagram, which is the mission is success, which I again highlight here, and that success basically depends on both of them. If you remember this last slide, it says both of them being true. So, which means that if both of them are true, then you would basically have a success for this mission. While the other 3 information sets which you have is 0 1, 1 0 and 0 0, if all of them are equally true means these are the 3 combinations which you have, then the mission is a failure, as I am now highlighting. So, if this is the case, this diagram basically very simply gives you an idea that out of the 4 combinations for the 2 vehicles, which means for vehicle 1 yes and yes, you have a success. For vehicle 1 no and vehicle 2 yes is a failure. For vehicle 1 it is yes 1 and vehicle 2 is a no, is a failure, and obviously the last one being vehicle 1 is a no, which is 0. I am 0 no, I am basically repeating but with the same essence, and vehicle 2 is also no, which is a failure, it is a failure. So, here basically the diagram as pointed out. Now, let us consider a different scenario. Again, is the space mission consists of two vehicles. Now, it says in the second bullet point, which is important to note, as I noted that both of them should operate in the last example, both of them should operate successfully for the program to be success. Here it says that at least one of the vehicle must be successfully launched, which means now the combinations are exactly the same. That means yes, yes for vehicle 1, vehicle 2, yes, no for vehicle 1, vehicle 2, no, yes for vehicle 1, vehicle 2, and no, no for vehicle 1, vehicle 2. But the outputs which you will get for this second example would be totally different from what you had in the first example, which you have just discussed. So, let us see how it is there. If you see it, it looks complicated, but the overall sequence is very clear. So, here on the left hand side, I will again highlight. So, you have vehicle 1 and vehicle 2, and on the right hand side you have basically the mission is a success and mission is a failure. The way they have been depicted, this triangle and this triangle with a line or a hemisphere, all these things are based on the fact that what is the input 3 criteria and the output 3 criteria, 2 criteria which you have, this 6 combination which I did discuss when we started the GERT concept. So, the first line which you should concentrate is this one. This is a success for vehicle 1, this is a success for vehicle 2. Now, the extreme one, which was an unsuccessful launch for vehicle 1 and vehicle 2 combined together, and if you separate them are these points. I am highlighting it using the yellow color. This is an unsuccessful launch, so it comes here. So, mission is a failure, and this one is also an unsuccessful launch such that mission is a failure, which means that both of them being false false gives you the answer as false, but any one of them being true, as mentioned in the problem statement, that one of them being true basically would be successful with that project, would lead to the mission being success, which I will try to now highlight in the red color. So, this is the mission being successful. So, let me see if I can basically highlight using the color. So, this is now yellow, I have tried. So, it basically is this is a success and this is a failure, which I am basically marking with a cross. Now, so they would be one path to failure and 3 paths to success. So, let us see them. So, one path to failure is this one, which I am again just drawing this line failure. Now, if you see the successful combined with the unsuccessful one is, let me use the red color, it will be much easier for us to highlight. Yes. So, vehicle 1 is a success, it goes in this line. Vehicle 2 is, say for example, not successful. So, maneuverability and not successful is there. So, is basically coming here. Vehicle 1 being maneuverability being a failure. So, this is a maneuverability being a failure, which will basically come here for vehicle 1, and vehicle 2 maneuverability being failure would basically come here. So, if both the vehicles are successfully launched, then what you will have is a combination which will lead to the case that any one of them being successful would lead to the end of the project, which means that if you go back to the earlier slide of the AND or exclusive or inclusive or concepts, they would be brought into the picture such that it gives you a very good idea that how the overall project can be drawn. Now, I want to lay some stress here that whenever you have more than 2 such logical operators like A, B, C. So, what you will do is that you will very simply follow the logical sequence of the operations, check whether A and B, I am giving you an example, see for example, A, B and C is there, and both of them basically have the XOR concept between A and B, and this concept of A, B combined has the AND. So, what you will do is that, and consider there would be such pile up of such operations coming one after the other. So, the logic followed is exactly the same. First you will basically concentrate on A and B, use the concept of XOR, which is the exclusive OR concept, and then find out what are the results. So, obviously there would be 4 results as we considered. So, that means A being 1, B being 1, A being 0, B being 1, A being 1, B being 0, and last combination being A and B both being 0. Based on that you will have that operations. Now, consider A and B has those 4 outputs and consider this as D. Then what you will do is that you combine D and C, considering that D has those 4 outputs as a combination of A and B, and then consider that A is B is out of the picture, take the 4 outputs of D, combine them with C, and then using the concept of AND operations, and then proceed accordingly. So, if you have basically a set of operations, go step by step such that it makes logical sense how you can combine them automatically. So, now consider the looping concept is coming. So, here consider a very simple GERT or GERT diagram which you have. In the first node, which I am now highlighting, basically gives you the problem definition, which is basically from node A to node P, the work is being done. From node B to node C, so this is A, this is B, this is C, and this is D. You have the research activity. Consider this basically a simple research project or R&D project which you are going to take. And then the combinations of basically going from C to D is basically you evaluate the research and get and have the project finished if it was a per 10 CPM. So, these loops which I am now highlighting were not there. Now, the moment you bring the loops, the things become complicated, but they give you a much better answer. So, the loops are what you see in this diagram is going from D to B. That means, when you draw the precedence concept, this precedent concept would also consider the fact that B would technically be followed after A, but there would be a feedback loop also coming from D to B such that this solution which is acceptable or unacceptable in the repeat research, that feedback which is highlighted here as I am highlighting, that feedback would come into the stage B such that you can get that feedback from D and utilize that to further enhance the process going from C to D. Similarly, this feedback which you get, if that is a major one from D, which means that you have to go to the drawing board and again redo the whole problem. So, you have to redefine the problem such that you go from B to A and start off the whole process from again from A to B, B to C, and C to D, such that this looping concept which you have gives you a very clear picture that how the work is going on. So, when you consider the GERT and the looping concept, this looping concept would be considered in such a way that if, say for example, the success rate is less than 30%, so obviously it means the looping will start, which means the probability that the path will be followed or not followed, considering the AND, exclusive OR or inclusive OR, and the 3 plus 2, which means 3 into 2 combinations which you have for the 3 inputs and the 2 inputs for the logic of operations would make sense, such that you can consider this looping concept in a big way and in a very logical way. So, it is important to note, however, some of the inherent disadvantage in the use of GERT precedence diagram. I will come into the actual problem later on, but let me just go into the concept in very general details. The first, GERT typically employs activity on arc formats. So, activity on node and activity on arcs may be one of the reasons that why it will be possible for us to consider the looping concept. So, if the looping concepts are not there, which means then trying to convert the job onto a node or jobs onto an arc is very simple in the per 10 CPM concept. But the moment you have a looping concept means that some feedback, some work is being done, which means that you cannot join or basically put one node on the other. So, obviously, the nodes would be the stages where you want to finish, or what is the stage where you are starting, or which is the stage you should take a stock of the situation of how the project is being completed, that should be done. And the feedback loop which will come would basically entail some work. So, here in that case the activity on the arc format would be applicable, because those arcs would basically entail some huge amount of work which is not part and parcel of the GERT network. So, let me continue as the second point. The first, the GERT typically employs activity on arc formats, which I explained, which we have previously noted are not at all common with modern project management techniques. So, the project management techniques which we did discuss in some details for the PERT and the CPM, we basically consider the activity in the arc and activity on node as the important concept based on which we could proceed, but that becomes a problem when we come into the GERT framework. Point number 2, the dummy concept which we had, the dummy jobs, which I did not discuss in the problems, but I did mention in some way that dummy jobs would basically be connecting two nodes, such that they gives you a logical sequence of the activities which is there. So, this dummy jobs or activities is only possible when you have the concept of the activity on the arcs one. So, hence trying to bring the dummy jobs using the node concept may not be possible in the GERT framework. Thus, with some few exceptions, GERT is not supported by common project management soft tools. So, you have to basically do your own calculations, but it gives you, if you are able to draw the diagram on a piece of paper with all the details, that gives you a very clear concept that how the logical operations between job 1 to job 2, between job 2 to job 3 and so on and so forth are taken into consideration such that point 1, the logical operations are taken into consideration. Point 2, the probability of a path coming up or a node coming up is taken into consideration. Point number 3, the time which may be probabilistic can also be considered as an attribute. Point 4, the looping is also considered, such that we get a much more realistic picture of the overall project which we are undertaking. Further, GERT network can become extremely cumbersome and complicated, as rightly pointed out in the diagram which we did, that two vehicles both firing or both being success leads to the completion of the launch, or else in the second example we considered that one of them vehicle being success would basically lead to the success of the project. So, if there are more vehicles or more complicated sequence of jobs, obviously the overall project becomes very complicated. If somebody is able to draw it to the maximum possible details, obviously it becomes easier, but generally it is very difficult to do that. So, it says that further GERT networks can become extremely cumbersome and complicated depending upon the size of the project, the number of activities expected, the feedback loops, the probabilistic condition that must be modeled, so on and so forth. Thus, although purporting to offer a more accessible visual treatment of project networks, GERT actually quickly becomes unwieldy and very difficult to draw, and obfuscates the visualizations of the project's network activities, such that in the overall scheme of things, if somebody is considering the overall macro project, trying to go into the details of the micro level becomes very complicated many of the time. So, I will just give a very brief definition of Q-GERT, which is queuing GERT, with a notion that I will again discuss the simple problem of GERT in the 36th, 37th, 38th, 39th and the 40th sorry, this is the 36th one. So, in the 37th, 38th, 39th and 40th class. So, Q-GERT is a modification of the traditional GERT approach, in that it recognizes special circumstances where multiple numbers of project teams or activities must be taken into consideration when trying to do the work. Q-GERT gets its name from the special queuing concept, which it has available for modeling situations in which queues build up prior to project activities. So, what is that? I will try to explain here. Further, Q-GERT allows the modeler to assign unique network attributes, that is activity times, nodal branching probabilities, what is the probability that the branching will happen, branching will not happen, to each of the individual projects, and then process these projects through a single generalized network. So, let me give you an example in very simple terms. Consider you have 3 jobs which are lying. So, So, 3 jobs, let me mention them A, B and C. Now, consider there is only one machine. So, if there is only one machine, it may be possible that all 3 A, B, C come and are there at the same time. So, if they are at the same time, consider this is a grinding machine, all jobs A, B, C have to be grinded. So, if I consider the logical sequence, I will basically start with that job which has the minimum time of operation, because if I do not take the minimum one, what will happen is that if I take the maximum one or somewhere in between, like minimum and maximum, consider A has the minimum one, consider time taken is 2 minutes, 2 hours, whatever it is, B has 3 and C has 4. So, if I take 4 then and then proceed in any sequence, the waiting time which is to be taken by the jobs in totality would be the highest. So, if I follow the sequence of 4, 3, 2, that means time sequence, so that means C, B, A, then the time taken by the jobs A, B, C collectively is the highest. Even if I take the sequence of 3, 4, 2, then also the time for the waiting time is high, but not as high as C, B, A. But if so, you can calculate it. Why? Because if I do the work of 4 minutes, which means job B has to have waited for 4 minutes, job A has to have waited for 2 minutes. Then if I do B, which means job A has to have waited for 4 plus 3 minutes. And when I go into basically the job A, the total time spent for the average waiting for A is 4 plus 3, waiting for B is 4. But if I follow the sequence in this order like A, B, C, then the time waited for B is 2, time waited for C is 2 plus 3. Why this 3 comes? Because 3 comes when B is being processed, A is already over and C has to wait. So, this sequence of jobs would basically depend that what is the processing time. Now, obviously, many of you who are quite experienced would say that what if I have to basically use some jigs and fixtures in the shop floor. So, obviously, the replacement of the jigs and fixtures and all these things would be coming into the picture, so that it will give a much more practical flavor, but trying to solve the problem would be difficult. Another way can be, say for example, they are coming in different sequences. So, if they are coming in different sequences, so those sequencing and scheduling has to be considered in such a way that the overall either the processing time or the overall average waiting time or whatever the metric we are trying to utilize has to be minimized in the best possible manner in order to meet the requirement of the overall jobs or the activities or overall project. So, with this I will close this 36th class and then continue with my 37th, 38th, 39th, 40th class on these 4 lectures which are left of half an hour each, and consider in a little bit more detail the concept of GERT, Q-GERT with very simple examples, such that they give you a flavor to the candidates and the students that how PERT, CPM are fundamentally different from GERT and Q-GERT, and how GERT and Q-GERT can be utilized in a very practical sense, even though it may be difficult to implement them in a practical sense, to bring the flavor of the practical problem which many of us face when trying to implement a project in the realistic sense. Thank you very much for your attention, and I am closed today. Thank you.